So today we are welcome to have Matthew Hastings from Microsoft Research, and he will be telling us about the sum of squares method for fermionic systems and the ground states of SYK systems.
Yeah, before we start, I want to add one more thing. First, before people join, Matt encouraged questions, so I hope there will be many questions throughout the talk. And two more announcements. It should be clear we will not take the speaker to dinner. However, at 4, Matt agreed to be in an informal chat at the same Zoom link. So then this will give us another opportunity to talk informally, what we would normally do with a seminar speaker who comes in person. So now I think we can start.
Okay, great. Thank you. So this is mostly going to be based on work that I did a couple of years ago with a collaborator, Ryan O'Donnell. Yeah, I just want to reiterate, please ask questions. Ryan has a recorded talk on YouTube about this topic, and he probably did a better talk than I'm going to do. So if you just want to sit there and not say anything, you should just go look at his YouTube video and not go to this talk. So instead, please ask questions and there'll be some benefit. So hopefully this will be of interest to a variety of audiences. There'll be some connection to computer science, some to quantum information and condensed matter physics. And I don't know if anyone can tell me if there's any relation to high energy physics or not, but I would be very interested if someone could tell me if there is. So let me begin with kind of generalities. So the general problem in any kind of physics or quantum chemistry or whatever is often, given a system of fermions, what is the ground state energy? There are other things you could ask, but that's sort of one of the most basic standard questions. And a general method for doing that is, maybe the system's exactly solvable, but in real world, often it's not. So a standard method is an upper bound method, a variational method. You write down some wave function, maybe it has some parameters you can adjust, and the wave function should have the property that you can efficiently, in a reasonable amount of time, to be precise, say polynomial time and the system size or something, evaluate the expectation value of the energy in that wave function. And having done that, that provides an upper bound for the true ground state energy. I want to tell you about a completely different method that instead is a method of computing lower bounds for ground state energies. So let's say one has some Hamiltonian H, and this could be very general. It doesn't need to be a fermionic Hamiltonian or whatever, but just some Hamiltonian. Could be acting on spins or whatever. And suppose you find some way of writing the Hamiltonian as the following form: lambda naught, which is some scalar, plus a sum of squares, sum over some discrete index alpha, and then you have some operator O alpha, and you write O dagger alpha, O alpha. Suppose you found a way of writing H like that. Someone gave you an H, and you find that you can rewrite it in this manner. It's equivalent to this. Well, that immediately implies that H is greater than or equal to lambda naught, that the true ground state energy is at least lambda naught, and possibly even bigger, but it's immediately a proof that it's at least lambda naught. This is a different method. This kind of method will give lower bounds to the ground state energy. Let me explain a little bit more about this method by talking about a classical system. So a classical system, I'm going to write it using quantum terminology, but let's say a classical system. So we have H, it's going to be, say, an Ising model. Sum over I and j, jij, which is some matrix, zi, zj, and these zi, zj will be some variables that are each plus minus 1. And the goal is to optimize the energy of this thing. Now, suppose then that you can write H equals lambda naught plus a sum of squares. And now I don't actually need to include the dagger. I can just write H equals sum over alpha O alpha squared. Because since this is a classical problem, we're going to write everything using commuting variables, and there's no reason to include both the O and the O dagger. We can assume that O is Hermitian in this case. In the quantum case, it's useful to take non-Hermitian O. Here, it's suffice to take Hermitian O. And now, well, what variables should we write here? Like, what should these operators be? What should these operators be? Well, let me just first point out that if we allow these operators O alpha to be completely general, if you could write down any operator here, any O alpha, then this method is able to prove that the ground state energy of H is at least what it actually is. So let's that the method is sufficiently powerful. I mean, this method gives lower bounds, and you might say, well, is the lower bound that this method gives, is it the same as the true ground state energy, or maybe it's far below it? Well, so suppose the true ground state energy is some E naught, Well, then H equals E naught plus square root of H minus E naught squared, like that. And now I've written as, so for lambda naught equals E naught, I've proven that the ground state energy of H is at least E naught. But this square root of H minus E naught may be some incredibly complicated operator, so it's assuming the true ground state energy of H is at least E naught, H minus E naught is positive semi-definite, so its square root is a Hermitian operator, and so we can write it like this, but this might be too complicated. So a weaker thing might be to say, try O alpha equals degree 1, say linear in these variables Zi. So if the true ground state energy is something, this might give us a bound that's below the true ground state energy, but gives some kind of reasonable bound. So we might try to write H as the sum of some scalar plus some degree 1 things, Z1 plus Z2 minus 3Z3 squared, plus then Z2 minus Z4 squared, plus and so on, a sum of configurations like this. And when we do this, you'll use some constraints given by the algebra. You'll use that the square of these variables is 1, and we'll use, since this is now the classical case, that they commute with each other. And so you could try to solve this problem. So you could say, assuming that these O alpha are at most degree 1, so it's a much smaller set to optimize over, let's try to find the best decomposition so that it gives a way of writing H. There may be many ways of writing H, many ways of decomposing it like this that are all equivalent because of this algebra relation. Like I could write Z1 squared, and that's the same as Z2 squared because that's both 1. So there's a lot of ways of writing it, and find the best possible decomposition of this. This might seem a difficult problem to optimize over. You might say, how do I optimize over this? How do I, even if I've restricted it to degree 1, how do I optimize over it? But the nice thing is that this is an instance of what's called a semi-definite program. And semi-definite programs can be solved, quote, solved in polynomial time. There's kind of this like lore that you can solve them in a time that's polynomial in the number of variables here. There's some technical caveats, but basically, yeah, you can solve these things efficiently. In practice, it gets slower and slower. You might say, okay, maybe we'll try O to be not degree 1, but degree 2. So O degree 1 gives us a certain bound. O degree 2 might give us a better bound. So this is important to understand, right? Like when O is degree 1, O squared is degree 2. If O is degree 2, O squared might be quartic, but there might be some cancellation so that the overall H that's left is just this quadratic H. So you can actually obtain often a better bound by allowing O to be quartic or higher degree than that, and so on. As the degree goes up, it's going to get less and less efficient to solve. But this is an instance of what's called a semi-definite program, and I'm going to explain it a bit more. Any questions up to here? Everyone good? Okay. So what do I mean a semi-definite program? I'll explain semi-definite program, but I'm going to give the dual form of this. Semi-definite programs, just like linear programs, have a certain duality theory, optimizing a certain semi-definite program, which is like maximizing something. Here we're trying to find the largest value of lambda naught such that you can write it this way. There's often a dual program, which is minimize something else. And in this case, the two happen to be equal. The max of one is exactly equal to the min of the other. And I'm going to write the dual semi-definite program down. And it's a clear way of explaining what a semi-definite program is. The original one, I can explain how that's a semi-definite program, but let me give the dual form. The dual form is, suppose you had some state, some mixed state. If we're doing quantum systems, this would be a quantum density matrix. For classical systems, it's just, a classical mixed state. Some probability distribution over different configurations. You could write down expectation values for these operators, Zi, Zj. And you could write this down as some matrix, Mij, which would be the matrix of expectation values. So the true ground state is going to have a particular matrix of, come on, focus on that. There we go, focused. The true ground state's gonna have a certain matrix of expectation values. So what do we know about this matrix? Well, we know things like Mii equals 1 because Z squared equals 1. We know Mij equals Mji So we have some linear constraints on it. The diagonal entries are 1, and the ij entry is the ji entry. And we know that this matrix is positive semi-definite. All of its eigenvalues are non-negative. It's a Hermitian symmetric matrix, and all of its eigenvalues are non-negative. Why do we know that? Well, if it had a negative eigenvalue, then you could write down some particular linear combination of the zi corresponding to that eigenvalue, and the expectation of the square of that operator would be negative. It would be saying, oh, the expectation, like if, you know, a certain eigenvector will read off a certain linear combination, and then that would say the expectation value of the square of that linear combination is negative, but the expectation value of every square of an operator is non-negative. So this matrix is this is a very important point to understand. So if there's questions, please ask. And what do we want to do? We want to say take this H subject and this matrix M. It's a matrix subject to these linear constraints, subject to the requirement that it's positive semi-definite, and we want to compute the minimum of the trace of M with this matrix J. And this is what a semi-definite program is. A semi-definite program is you're given a matrix, you impose the constraint that the matrix is non-negative, you impose any linear relations you want on the matrix. These are the linear relations we impose here, and you minimize some linear function of the matrix. That's a semi-definite program, and it can be solved efficiently. And there's a dual semi-definite program, which actually has the same form. It's maximizing some linear function of some other matrix subject to other linear constraints. The dual form is writing it as the sum of squares that I was mentioning. This form is this. So this gives, the minimum of this gives, again, some lower bound on the ground state energy, because if you minimize over M, you get some particular configuration of Zi, Zj. It's going to give an expectation value that's no bigger than the true one, because the true expectation value of Zi, Zj obeys all these constraints, but it may obey additional constraints that this doesn't know about. And so this may be less than the true ground state energy. And in fact, even in some simple examples, a very simple example to do is to just take 3 spins with completely frustrating interactions. So anti-ferromagnetic interaction between each pair. And if you go calculate it, you'll find that it gets the wrong value for the ground state energy. Essentially, it gets the value that you would get if you thought the spins were XY spins, that instead of pointing up or down, they can point in the plane. So one can point that way, one can point that way, and one can point that way. It gets that value. But it's not perfect, but it's reasonable. There's a general result that for this kind of Ising Hamiltonian, there's the true ground state energy. This can give some value. It sort of certifies that the energy is at least something. And there's a method of rounding. If this gives some value for the ground state energy, you can round it to something that's not much bigger. You can come up with a true solution, like an actual set of Zi, Zj, that's expectation value of the energy is not much bigger than what this certifies it as. So this can't be much worse than the true one, because when you round it, it doesn't go up too much. So it started really far below it, you round it, you get something impossible. So there's some whole result that this gives the optimal, well, it's believed that this kind of gives the best possible approximation algorithm for this kind of Ising model, best in a certain sense. It's believed actually that going to higher degree may improve the performance for specific problems, but in general for the classical model, that really nothing can do better than this. And it's kind of an active area of research. Like people talk about fooling, like, oh, if we go to a higher degree, maybe it's able to figure out certain problems, but we think there's still other problems that fool it and it misestimates the energy. So it's an active area of research. So that's kind of like the classical background. Any questions up to here? No? Okay. Now, of course, we want to do, oh,
I have
yeah.
a question.
Yes.
Did you well, it seems like you did not use any notion of locality. The spins are not ordered in any way.
Exactly.
So
Yes.
any random matrix J would do the job.
Yes.
If you assume that they are ordered in some form, can you do better?
Yes, what you can try to do, yeah, I mean, this is a very good question, because this method I think is particularly useful when there is no locality. But what you can try to do, I said in general, one thinks that you can always fool any degree, but for specific practical problems, as you increase the degree of the approximation, you do better. But if you say, okay, and what I mean increase the degree of the approximation, that's either allowing squares of things that are above linear, or in this dual formulation saying, oh, I also want to track like expectation Zi, Zj ZK, ZL. And I can write this as a matrix whose like row column index is IJ, his row index is IJ, and its column index is KL. And then that'll be subject to lots of linear constraints because like IJ, commute, and so on. So it's a bigger matrix. And when you do that, that's going to do better for lots of specific problems. So you can go to higher and higher matrices and do better and better, but your computational cost goes up. But what you could try to do if you have locality is you can say, well, I don't want to track all of these. If I have n spins, this might be n to the 4 of them, but maybe I'll only track it when I is near J and K is near L. And so it's still order n squared things. And so people try things like that. So it's sort of like, what expectation values should you track? And you can put in your physics intuition to track certain expectation values.
A question?
Yeah.
Just to be sure I understand, what is not taken into account is the fact that M is expectation value of plus minus 1 valued spins. Is that the point in this particular example?
Yeah, I mean, what's taken into account is essentially that M is expectation value of spins whose mean square is plus minus 1, but it doesn't know that every single time it has to be plus minus 1.
Thank you.
It's essentially solving the large n spin glass is what it's solving.
Yeah.
Now, if you go to quadratic degree, quartic degree, higher degree, it gets better and better and knows a little bit more. But the belief is that for any fixed degree, eventually there's still something fundamental it doesn't know.
Mm-hmm. Thanks.
Well, excuse me. Then there's the max cut is a problem which is related to this, right? And then that's not soluble, at least for all sort of graphical situations. You get close, but you can't always solve.
Exactly. Yeah. So this is believed to be sort of the best approximation. There's a belief that this is the best approximation, but it's going to only get a constant factor. But that's kind of non-trivial that it'll get a constant factor. You know, it'll get within like 80-something% of the optimum cut always, which is great. This ability to round it, this ability to take this pseudo expectation, it's called, this expectation ZIZ thing that obeys some constraints but not all, and then round it to a true expectation value. Come up with something that's really a true expectation value.
Thank you.
Okay, so we want to do quantum mechanics. You could do these for qubit systems. You could look at Hamiltonians that are sum of like x on qubit I times y on qubit j, stuff like that. You could do that. That's adds something, but there's still some kind of approximation you can make, essentially the same kind of approximation that can't be too far off. I can talk more about that, but really I think the thing where it gets really interesting, you can prove that you can't, just like you can't too badly fool the classical one, you can't too badly fool the quantum version with qubits, where the Hamiltonian is a sum of like x1, y2, stuff like that. But the really interesting case, I think, is to talk about fermionic systems. And kind of as a paradigmatic example, let's talk about the SYK model. So this is going to be a Hamiltonian of the following form. SYK, Sachdev-Ye-Kitaev, like that. So this is a particular Hamiltonian. So these gamma I are Majorana operators. So the square of each operator is 1, gamma I, gamma j. In fact, anti-commute if I is not equal to j. So the anti-commutator of 2 of them is 2 delta ij. If you come from a condensed matter physics background, a way to think about this is that you have fermion creation and annihilation operators, and you can say gamma 1 is psi dagger 1 plus psi 1, and what do you have to, like 1 over square root 2 or something like that? I'll probably get the square root 2 wrong. Gamma 2 is I psi dagger 1 minus psi 1. I think that's right. I think there's no square root 2. Then gamma 3 will be psi dagger 2 plus psi 2, and so on. So it's just a linear combination of creation and annihilation operators. So here's this is the SYK model. And there's a whole bunch of lore that people in the audience probably know a lot more than I do. So I'll just say, like, I've heard things that this is like, oh, well, okay. In J, if we just wrote down any J, it would just be a very arbitrary model. The SYK model is choose J par random such that the L2 norm is fixed. So just, or you could say choose the entries of J as independent Gaussian variables, such that I'm going to choose a non-standard normalization, and I apologize for doing this, such that the L2 norm of J is 1, such that the sum of squares of entries of J is 1. This is a little bit different normalization, so my normalization of the ground state energy is going to be off by a factor of square root of the number of modes from the usual one. So just non-standard normalization, so just calling attention to that. This just fit a little bit better with the computer science literature and my co-author was a computer scientist, so we stuck with this. So if you choose it at random, this is the SYK model. Now you could just say equivalently, like each entry of J is a Gaussian random number, and then such that the variance is 1 over the number of modes, or 1 over the number of modes to the 4th. Okay, so this is the SYK model, and there's a whole literature like that. This is sort of the most random, most entangling, fastest scrambling Hamiltonian out there. That it's supposed to be like incredibly non-local in some way. So let's talk about trying to say something about the ground state energy. The true ground state energy is minus square root of the number of modes with some constant in front. There's some constant. It's minus proportional to the square root of the number of modes. We actually, I think our paper might be the first rigorous proof of that statement as an order of magnitude. Although there's actually enormous literature showing like that this is what you expect on physics ground, and even telling you what the constant in front should be. So this is the true ground state energy, and this is again off by a factor of square root n. You're probably used to, if you come from this science, used to seeing n rather than square root n. But this is the true ground state energy. So let's see what you can do with a variational method. With a variational method, like what do you write down as a variational state? You know, it's kind of not obvious what variational state to write down. The first choice I think everyone would reach for is a Gaussian state. A Gaussian state. This is kind of a generalization of a Slater determinant. If you come up from a condensed matter background, this Hamiltonian with these gamma I, gamma j, it allows like particle number non-conserving things. So a Gaussian state, which is simply defined to be the ground state of a quadratic Hamiltonian in these of a quadratic Hamiltonian in these Majorana operators. That's what a Gaussian state, quadratic Hamiltonian, like sum over ij, let's call it Tij, gamma I, gamma j, and there's a factor of I in front to make T should be a Hermitian matrix, and then because gamma I, gamma j is anti-Hermitian. Okay, so that's what a Gaussian state is. And the nice thing about Gaussian states is you can efficiently evaluate expectation values. So let's say you have some Gaussian state, and let's call it psi GS for Gaussian state. And you want to evaluate the expectation value of the Hamiltonian in this state. Well, the great thing about this is that a Gaussian state defines certain expectation value of a pair like gamma I, gamma j, and then higher order expectation values just come from Wick's theorem. So by Wick's theorem, this is something like gamma j I j k l times the expectation gamma I, gamma j times the expectation gamma k, gamma l plus permutations, meaning different ways of pairing it off, like expectation gamma I, gamma k, gamma j, gamma l, or expectation gamma I, gamma l, expectation gamma j, gamma k. So let's just look at this first term because the other terms are going to be similar. This term looks a lot like a matrix vector product. Think of ij as a row index for a matrix, kl as a column index for a matrix, and then this looks like a vector, and this looks like a vector, and this looks like a matrix. So if we think of this as a matrix, we can go compute its norm, its operator norm, its largest eigenvalue. And now this is a standard exercise in random matrix theory. It's a matrix whose entries are Gaussians. Okay, there's some linear constraints on it, but related by antisymmetry like ij minus ji, doesn't really matter. It's a matrix whose entries are Gaussian. And so we just like appeal to random matrix theory results, and we can figure out what its eigenvalues are. It's an n squared by n squared matrix, so it has n squared eigenvalues. Its L2 norm is 1, so the typical eigenvalue is 1 over square root n. This is like ancient random matrix theory. So we know how big its operator norm is. Now, what is the norm of this as a vector? Well, if you think about it, a typical Gaussian state can be brought into a form up to some unitary rotation that it's like gamma 1, gamma 2 expectation value is 1, gamma 3, gamma 4 expectation value is 1, or actually all I, gamma 5, gamma 6 expectation value is 1, and so on. And if you go compute what its L2 norm is, its L2 norm squared is a sum over like roughly n different things, the 1, 2, the 3, 4, the 5, 6. And so its L2 norm is 1 over square root n, and the same for this one and this one. So if you go compute this matrix vector product, oh, sorry, not 1 over square root n, but square root n. There's n, roughly n over 2. Like 1, 2 can be perfectly paired, 3, 4 can be perfectly paired, 5, 6 can be perfectly paired. You can bring this expectation value to a block diagonal form, and there's n blocks, n over 2 blocks. So you get square root n from here, square root n from here, and then 1 over n from here. So the expectation value of this is only of order 1. It's the same for the permutations. So a Gaussian state does badly. It cannot well approximate the ground state expectation value of this Hamiltonian. Gaussian states are not good witnesses for the ground state expectation value. They're far off. Subsequent work, that was shown before Ryan and I, someone else showed that. So subsequently, it was possible to show even that, like if you take a Gaussian state and you take other things like you apply only logarithmically many steps of Langshos to that, which is something where you could still efficiently compute it, it still does not work. So basically, we do not have, and I've not seen anyone write down a witness where you can efficiently evaluate the expectation value in that witness. You can actually efficiently evaluate, like, here's the witness. I can actually efficiently compute the expectation value of this Hamiltonian in the witness, and it can get an order square root n energy for the ground state. And so hence prove that the ground state energy is minus square root n or smaller, give some upper bound on the ground state energy, which is the right order of magnitude. I have not seen any witness that can give a upper bound that is the correct order of magnitude, at least a classical one. Okay, so that's one of the reasons that this problem is hard. So I want to talk about, and since now start talking about some new results with Ryan. I want to talk about an idea that a way to think about what it means to like come up with a witness and prove this. There's a fairly simple argument that the largest eigenvalue of H is of order square root n. But it's a fairly simple argument that if you take a random H, probably the expectation value is of order n at most. Like it's an argument that, but it doesn't, I don't know that I'll give it, I'm not sure I'll have time to give that, but it's by previous people. It's just based on looking at like powers of H and bounding them, bounding the expectation value of high powers of H. The trouble is that kind of argument, I don't know how you can take a specific H and point in a specific H and say, oh, we're going to prove that for this specific H, the ground state energy, its order of magnitude is at most square root n. It's not like n or something bigger. So what we are searching for is what we would call a certification. We want an algorithm that if you give it an instance of SYK, it either can prove by giving some efficient classical proof that the ground state energy is of order of magnitude minus square root of n or bigger. It's not minus like n to the 3/4 or something like that, but only minus square root n or some larger amount, doesn't know how much more. Or it answers, I don't know, I can't prove anything, but it gives the proof on 99% of SYK instances. Like almost every time you give it an SYK instance, it can give a proof that the ground state energy it's the absolute value of the ground state energy is at most the right order of magnitude. And as you can guess, the answer is going to be the sum of squares. So I'm going to give a proof that the sum of squares knows this. Not the degree 4 sum of squares, but a higher degree one. Oh, so degree 4 sum of squares means like, so we would write H as sum, just to explain what we mean by degree of sum of squares. If each of these O alpha is degree 2, meaning it's quadratic in the Majorana operators, this is called the degree 4 sum of squares because the total degree is 4. That's the same as saying you keep track of expectation values up to gamma to the 4. If each of these O alpha is degree 3, this is called the degree 6 sum of squares. And what I'm going to show is that the degree 6 sum of squares is able to give a lower bound for the ground state energy that's the right order of magnitude. So how do we do this? So I'm going to rewrite the Hamiltonian as sum over I, gamma I, tau I, where tau I is defined to be sum over j, k, l, j, I, j, k, l, gamma j, gamma k, gamma l. So thus far, this is just rewriting the Hamiltonian in some, tau I defined to be, this is the equal sign there. This is just rewriting the Hamiltonian in some equivalent form. Now we can apply Cauchy-Schwarz. This is basically something that sum of squares knows. I'm not going to like actually write down the solution of the semi-definite program. I'm just going to do some math and at certain steps tell you like, yeah, the sum of squares knows that, it knows how to do this. So one thing it does, and one thing is that the expectation value of H then is bigger than by Cauchy-Schwarz, or let's talk about the absolute value of the expectation value. We'll bound the absolute value of the expectation value is less than by Cauchy-Schwarz, the square root of the expectation value of sum over I gamma I squared, square root of the expectation value of sum over I tau I squared. And sum of squares knows Cauchy-Schwarz. That's sort of, if a matrix kind of didn't obey this, then it would be not positive semi-definite somewhere. So it knows this. And because it has these linear relations, it knows that gamma I squared is 1. So the sum of them is n, so square root. So it knows that this is square root n. And so now it needs to figure out what this thing is. But you have some linear relations again. Tau I is degree 3 object. So tau I squared looks like a degree 6 object, but there's some anti-commutation relations in there. And if you have a term in tau I that's like gamma 1, gamma 2, gamma 3, another term that's like gamma 4, gamma 5, gamma 6, let's say it's the linear combination of these two, gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6 is minus gamma 4, gamma 5, gamma 6, gamma 1, gamma 2, gamma 3. And so there's some anti-commutation relations. And when you work those anti-commutation relations out, this thing actually, tau I squared winds up only being degree 4. And in cartoon, it looks, tau I squared looks something kind of like what I could draw like this diagrammatically. This diagram doesn't really mean anything formal, but is intended to be a little bit suggestive. Each of these vertices is this JIJKL. You have some interior index J that you sum over. These dashed lines would be index L. And this would be like gamma J, oh, sorry, gamma K, gamma L, gamma M, gamma N. That is, tau I squared looks something like JIJKL, IJKL, JIJMN, gamma KL, gamma K, gamma L, gamma N, gamma N, like that. Okay. And now we have to sum over tau squared. Sorry, sum over I. So what you get actually in here is the expectation value of the sum over I and J, JIJKL, JIJMN, gamma J, gamma, sorry, gamma K, gamma L, gamma N, gamma N, and its expectation value, like that, like that. This is what you get right here. And so this looks a bit like we just join these like that. Okay. So the nice thing is this JIJKL, JIJMN looks like a matrix multiplication. If you regard, this is like a row index, column index, row index, column index. It looks like you multiplied the matrix J by itself. And since J has operator norm 1 over n as a matrix, with high probability typically it does, and that's something you can efficiently check. It's easy to just classically go compute what its operator norm is. The operator norm of this thing is 1 over n squared. So you have some matrix with operator norm 1 over n squared. Its operator norm is of order 1 over n squared. And then you're multiplying it by this expectation. Let me slide it up a little bit so we can see. And you're multiplying it by this expectation value. This expectation value is some other matrix. And what you can do is say, okay, so we regard KL as a row index, MN as a column index. And it's positive semi-definite and its diagonal entries are 1. It's an n squared by n squared matrix. So its trace, it's a positive semi-definite matrix whose trace is n squared, of order n squared. So if you take that thing, positive semi-definite trace order n squared, multiply it by something operator norm 1, this whole product is of order 1. This product is order 1. So this implies that this whole thing is less than square root n. Okay. So this allows you, basically all you have to do is go, as the most efficient thing is you can just go take this matrix J and compute what its operator norm is. And then if it's not bigger than 1 over n, that immediately proves that the ground state energy in absolute values at most square root n. So, and with hyperbole is the case. So there's your algorithm. It's an instance of the degree 6 sum of squares. You could also run the full degree 6 sum of squares or just compute this. It's like the degree 6 sum of squares knows this, but it knows other things too. Questions up to this point? This was probably like the most technical math part of this. So this gives classical witnesses that bound the ground state energy. It gives an alternate proof that with high probability, the ground state energy is at most order square root n in absolute value. No questions? No. Okay. So yeah.
You don't have a an easy to check variational wave function that illustrates this. That's what you said before?
Right. So we don't have an easy, now I'm going to talk for a second. I'm going to talk in a second about variational wave functions. We don't have a classical variational wave function that gives an upper bound that's the right order of magnitude. But the sum of squares will give a lower bound that's the right order of magnitude. The method, I think it's related to what is called merons in the field theory literature. Or sorry, merons, something like that. These
Melon diagrams.
Yeah, melon diagrams. Okay, melons, not merons. Sorry, melon diagrams. Now I'm going to talk about a variational wave function, which is inspired by the same ideas.
Something. So far you discussed estimates, or is this an argument that gives an actual lower one?
This will give an actual number, but the actual number it gives is probably not going to be the correct prefactor. The lower bound that's, I don't know, twice that,
Okay.
maybe the true ground state is, minus or whatever it is. There's some, 2 on pi, whatever it is, there's some number, and this will give a number that's maybe like twice as big or something as the true lower bound. As its guess at the lower bound.
So there's something basic I'm missing. Where are you keeping track of the sign of h? So you say mod of h has to be order square root n, but is it important because the Gaussian already had order 1? So
sorry, what was the question?
Can I not be heard? Do I have to come front to be heard?
Well,
So the question is just what about the sign of h? Isn't that?
The sign of h? Yeah, I mean, I was proving that the absolute value is at most this. This argument will both prove that the lowest eigenvalue is at least minus something times square root n, and that the highest eigenvalue is at most something times square root n. This is, yeah, it will prove either one. It doesn't really matter. We could say we want to minimize h or we want to maximize h. It's the same. It's really the same problem. What is the largest eigenvalue or what is the smallest eigenvalue? And I apologize if I was a little sloppy about talking, whether I was talking about like minus the eigenvalue or plus the eigenvalue. So that's why I said that there's, so the absolute value, the absolute value of the expectation is at most this. So that will prove that the true ground state energy, which is a negative number, is at least, minus 2 square root n or whatever the prefactor is. I don't remember what the prefactor is. It will prove that the true ground state energy is at least minus something times square root n.
the argument you just told us was an upper bound. I thought the sum of squares method would give us a lower bound.
Yes, sorry. So I know this is, I was maybe a little sloppy about what.
I understand about the models, but yeah.
The ground state energy is somewhere.
Yeah.
Right? The sum of squares, SOS lower bound is somewhere here. So this is minus some constant times square root n is the true ground state energy. The sum of squares lower bound is minus some other constant c prime times square root n. The best variational wave function is way up here, minus O of 1. The best Gaussian variational wave function is way up here, minus O of 1. But the thing that maybe I was a little unclear when I said is, I was talking about the absolute value of the expectation of h. And so equivalently, if you want to talk about the largest eigenvalue of h instead of the smallest eigenvalue of h, the largest SOS gives an upper bound for the largest eigenvalue, a lower bound for the smallest eigenvalue, and an upper bound for the largest eigenvalue. You do that by writing h as a scalar minus the sum of squares. That's how you can get an upper bound for the largest eigenvalue. And so if you look at the upper bounds, there'll be some SOS upper bound that'll be c prime square root n, SOS upper bound. The true ground state energy will be some c square root n. The true, not ground state energy, highest excited state energy. And then the Gaussian will be O of 1 somewhere here. So
both the highest and the smallest scale like root n. Yeah.
Exactly. Yeah, and they're exactly the same. And so, and sometimes it's easier to just talk about like the highest, just because I don't need to keep saying the absolute value or saying it's at least this. So let's just talk about the highest now from now on. So then SOS is giving upper bounds because it's writing H as something minus the sum of squares instead of something plus the sum of squares. But yeah, SOS is giving a bound that's like in absolute value is an upper bound. It's an upper bound in absolute value. Apologies for the slightly unclear notation. Other questions? Okay. Right. So of course, now the question is like, can we do better, right? Can we prove now also some bound here, like some bound on the ground state energy that will be the correct order of magnitude, some like, C prime prime square root n, with say perhaps a variational method or other method. So the best Gaussian wave functions don't do well enough. Langshaw's acting on the best Gaussian wave function doesn't do well enough. So the question is there anything that sits here? And we look for it in the same kind of certification sense, not a general result that with high probability, this is what the ground state energy is, but rather an algorithm that you can feed an arbitrary quartic Hamiltonian in, and it either says, I don't know, or it says, here's a proof that the ground state energy is, below this quantity. And 99% of the time it gives the proof, and only 1% of the time it says, I don't know. Is the question, can we do that? And I don't know any classical solution to that. I do not know any solution with a classical variational wave function that you can efficiently evaluate. But I do know a quantum solution. And the quantum solution is actually closely related to this sum of squares argument. So as you recall, we wrote the Hamiltonian as sum over I, gamma I, tau I, where these tau I were these degree 3 variables. And let's pretend that these tau I are actually kind of just like variational, sorry, not variational, like Majorana variables. So that would mean that tau I, tau j, that their anti-commutator is, well, what's the right order of magnitude? Right order of magnitude is a 1 over n in front, delta ij, and actually it's a minus sign in front because tau is anti-Hermitian instead of Hermitian. So this would be kind of a guess. Like we know roughly how big the expectation value of tau squared is. That's that 1 over n. The question, and let's pretend that the different ones anti-commute with each other. Of course they don't. I mean, these variables don't. There's some cubic variable in the Majoranas, some other cubic variable in the Majoranas. And so when you anti-commute tau 1 with tau 2, you get a complicated expression rather than 0. But like, let's just pretend. If this were true, if H were of this form, how would you go prepare its ground state? Well, let's introduce some variables chi I, which are actual Majorana variables. So actually chi I, chi j equals 2 delta ij. The chi will be like really actual honest to God Majorana variables. And then here's a quantum algorithm. One, prepare the ground state of the Hamiltonian H equals I, in factor of I because it's anti-Hermitian, sum over I, gamma I, chi I. So prepare the ground state of that Hamiltonian. And when I'm going to say prepare and evolve the wave function, these are all things that the quantum computing community has given efficient primitives to do, some way of like writing the Hilbert space here in some efficient way on a quantum computer, preparing a particular state on it, and then evolving the particular state in some way and doing it all in a polynomial time. And then what we would try to do is like rotate these chi variables into tau variables. So we could say like in quote, rotate chi into tau. What I mean is if these tau variables really obeyed this kind of commutation, anti-commutation relations, what you would do is you would take, so you prepare the ground state of this. Let's call this ground state psi naught, call it psi naught. And so then you would, to do the rotation, you would take this state psi naught and you would act on it with a particular unitary, and that particular unitary would be sum over some angle theta, and then chi I tau I. It would rotate it would rotate the chi-i's into the tau-i's when you apply this. And if the tau's actually obey those commutation relations and the chi's, they do by definition, then this would turn the ground state of this particular Hamiltonian here, gamma I chi-i, into the ground state of this Hamiltonian here, gamma I tau-i, by rotating it. Now, tau-i don't obey those anti-commutation relations, but let's just take this as a variational state. Take this thing as a variational state and has one variational parameter, the choice of theta. And what you can do is you can go compute what's the expectation value of it. So let's call this psi of the sine naught of theta. Define sine naught of theta to be this. You can compute the expectation value of the Hamiltonian in this state sine naught of theta. And there's a expanded in a power series in theta. There's a constant term, which is 0. There's a linear term proportional to theta. And then there's higher terms. And you can bound the contribution of the higher terms. Actually, rather than wanting a power series, what you want is the, this standard formula from calculus that like the error, that if you take the first derivative, the error between the first derivative of some function and its actual value is bounded by like the second derivative somewhere on the curve, right? So if I have a function that has a particular curve, and if you expand out the first derivative, the error here is bounded in some way by like the worst case second derivative along the curve. Actually, I should draw the function going the other way. What's happening is that as theta increases, the function energy is going the right way, but there's some second derivative term that might hurt it. And you can bound how big this second derivative term is, because this second derivative term is going to be, you can just write it down, it's some expectation value of some particularly complicated polynomial of the Majorana operators, some fairly complicated polynomial of the Majorana operators. And you can use techniques like this sum of squares and other techniques in the literature to upper bound the operator norm of that thing and bound, oh, this is how big this second derivative term can be. Now, you don't know that the second derivative term is going to be that for any specific instance, but typically the second derivative won't be so bad. So typically there's a choice of theta such that this psi naught has the right expectation value. So it serves as a quantum witness. You can write this state down, you can efficiently create it on a quantum computer, and then you can evaluate the expectation value of H in this state, and you get some random answer as you evaluate, but you can repeat it many, many, many times and convince yourself to high accuracy that, okay, we really have a witness that indeed has the correct variational energy. So we know a classical way. It's interesting in a sense that you might ask, like, what is the complexity of constructing a state whose energy is the right order of magnitude as the SYK state? Not the true SYK ground state, but something whose energy is of the same order of magnitude. What's the complexity of constructing something like that? And the point is that here is a quantum circuit that does it. I mean, I worry about exactly what the depth is, and I haven't thought about this, but it can be constructed in polynomial time, a wave function with the right order of magnitude, and then evaluated. So I'm going to stop here, and I'd really be interested in any kinds of questions or relation to other thing. I've been very excited about this kind of question. Like there's these tau variables, ways of writing the Hamiltonian that capture important fragments of the sum of squares. I've been interested in whether they might have some practical application in chemistry systems or other quantum systems, because this sum of squares method is quite powerful, but efficiently and while high operators are in principle efficiently evaluatable, if you want to start evaluating like degree 6 on a modestly sized system of like 30 or so orbitals, it's going to very quickly be an enormous amount of computer time. So while in principle it's efficient, these semi-definite programs wind up being fairly high order polynomials to solve. So I've been like interested in trying to explore more about these semi-definite programs, see if one can understand more to more rapidly solve them in various practical examples. But let me just close here and take any questions. Thank you.
I think maybe I missed it right at the end. So
you can understand analytically or parametrically or something that that the expectation value of H and psi of theta has the right scalar?
Yeah, for a particular choice of theta. Yes, yes, there is a particular choice of theta, and it's actually, you know, because it's a large random system, it's not like you need to pick it separately for each problem. There's like one particular choice of theta such that for almost every instance of the SYK model, or I should say with high probability, if you draw an instance of the SYK model, this choice of theta will give a state whose expectation value for H is of the correct order of magnitude as the ground state.
As you're varying theta, is it like is it not scaling with root n, and then for some special theta, like?
Oh yeah, the particular theta you choose does depend upon, and I forget, I'd have to check back the math in the paper. It's theta that's like some constant times. I mean, it's not hard to work out. Some constant times like 1 over root n or it's root n or something like that. Yeah, there's a particular choice of theta. Maybe it was theta proportional to 1. I don't know, but there's like a particular choice of theta so that the linear term in theta is proportional to square root n. And so that'll immediately tell you like what value of theta you should have, because it's okay. I want to compute, just take this wave function we got, compute its linear order term in theta, and see how big theta needs to be to get the correct order of magnitude. And so there's some theta of that order of magnitude, and then you look at the quadratic behavior, and we can bound how bad the quadratic behavior is. So there's some particular theta, and I have to either, you know, take 10 minutes to like redo the math or look in the paper to tell you what it was. But there's some particular value of theta, so that for that value of theta, the wave function has the right order of magnitude with high probability.
I mean, does that value of theta just comes from rescaling the taus, and so that they have canonical commutation relations? Then
Yeah, something like that. Yes, it's something like that. Yeah. You know, because maybe it's square root n because the taus are like of order 1 over square root n in some sense. So maybe it was of order square root n. Yeah, it's basically rescaling them so the canonical commutation relations are right. And then rather taking theta to be 1, you maybe need to take it to be like rather than taking to be theta to be like, you know, square root n, maybe you need to take it to be like 1 over 100 square root n or something like that, in order to like know that the higher order term is much smaller to really bound the next order term. But yes, it's exactly that. It's like however big it would be to rotate you're exactly right, to rotate the chi's into the taus, except a lot smaller, because you have to then you show that the second order term typically has the right order of magnitude, that it doesn't overwhelm the first order term, but you need to also make it like numerically smaller. And so I forget, you know, exactly what the right value of theta is.
In practice, how close does the coefficient of root n get to the known result?
That's another good question. I forget. I don't remember. We're off on both those by some constant numbers. Like I said, I think this might be the first actual proof, completely, you know, the first real proof that the ground state energy is actually this correct order of magnitude. Although there's certainly, people know what the right answer is. It's just, I don't think it's like proven what the right answer is. People know actually what the prefactor is. And there's a upper bound based on, there's a very simple way of proving like this thing that we proved with the sum of squares, which is to look at the trace of high powers of H. People, you know, you can say like, oh, let's look at trace of H to the K for some K. And well, this is a sum of all kinds of things. Or maybe I shouldn't use K because I'm already using it. Trace of, well, we'll use K. So it's a trace of various, like we'll use A, B, C for like gamma A, gamma B, gamma C, gamma D, J, A, B, C, D, and you know, so on. Then gamma E, gamma F, gamma G, gamma H, J, B. So it's something like this. And then in expectation, when you look at the trace of J, so it's something like this. So if you compute its expectation value, you can then, well, each of these J's, these entries are Gaussian, so you can pair them off. You can say, like, oh, well, this J, A, B, C, D must be the same as some other J, E, F, G, H somewhere else. And so you reduce it to just some combinations of gamma matrices, some sum of combinations of gamma matrices, and you bound how big each of those are using like just a very crude bound that like gamma is at most normal 1, basically. And that'll tell you, and use this to bound the expectation value of high powers of the trace of high powers of H. And that will allows you to bound the norm of H, because if H had a large norm, this trace would be too big. But it's just bounding the expectation, it's not bounding it for any specific choice. So here we have this certification that can bound for any specific choice, but I didn't know previously a proof, a lower bound on the norm of H. And so this variational argument gives that. But yeah, I don't remember how far off it is from what the correct value is. Probably, some constant factor of a few, probably. I don't remember. I think we were closer on our sum of squares bound than we were on our variational bound, if I remember right, but I don't remember how far off.
I did not understand what was the purpose of the quantum aspect of the algorithm. In the end, you prove the bound analytically, right?
Right. If you just want to prove the bound, there is no need to call it a quantum algorithm. The bound is there if you want to say, I regard this as a certification task. And so this is like, here it's speaking to a computer science audience. The question, or motivated by working with a computer scientist, since my colleague was a computer scientist. The question is, we have this problem, and can you give proofs of this? Can you give a proof that, oh yeah, this is, this something like the variational bounds. And if you are just a classical person, I don't know any way to convince you for a specific choice of JIJKL that, a variational bound that's the correct order of magnitude. But if you had a quantum computer, I could convince you. That's the statement. You could actually just check for yourself. But I don't even know like a way to convince you if you had a classical computer. So it's just that's a particular question of interest. Can you convince someone classical, or can you convince someone quantum that can you write down a wave function that has this property?
I think I missed something, but very, very, very basic. You just convinced us with no computers. I mean,
exactly. Okay. Yeah. I know what you're going to ask. Okay, good question. Yeah, I convince you with no computers, and so you're saying like, wait, why do I say we need a computer, right? Even you need a quantum computer, not even a classical computer. Convince you with no computers. What I convinced you with no computers is that if you run this algorithm, this quantum algorithm, say, typically the ground state expectation value is going to be a certain thing. Or sorry, not the expectation value of the energy in this particular state is going to be a certain thing. And the other thing I can
some very particular JIJKL, and you want to really prove for that
particular. Exactly. That's the exact point, right? So, if you want to know, and it's the same thing with the sum of squares proof. If you want to know, for almost every JIJKL that the norm of H is at most something, to prove what we did with the sum of squares, that's there's much easier ways of doing it. But if you want to prove, here's this specific one, and maybe there's some weird conspiracy, that's what you need it for.
Could I make
some other?
Yes, sorry. Could I make a comment about specific J? Like there are these non-random models, the tensor models, where J is fixed by some symmetry, like say ON cube symmetry. And
yes.
That's a similar model to SYK in the sense that it's dominated by melonic graphs. And we played with these type of sum of square bounds. And in the tensor model case, I think the simplest bound is not quite parametrically stringent enough, but we came up with a bound that's stringent enough. But J in that case is completely fixed, basically up to an overall constant. So.
Yeah, I think I read the paper you're talking about. I think I know your paper there.
Oh, good. Yeah.
It took us a little while.
Yeah, we played for tensor models and also like fermionic matrix models. Sometimes the bound is actually saturated, I think, but not for tensor models.
Yeah, I mean, one thing I would be curious about your model. Yeah, probably. I think some sum of squares witness may prove one side of the energy, and I don't know if you had a proof the other direction, the variational type, and I don't know if the kind of
I'm not sure. We definitely had tried the sum of squares, but the simplest attempt was not stringent enough. It just failed by a little bit, but then there was a way to fix it actually.
Yeah, well, to comment on the simplest attempt, one thing I didn't mention here, I don't remember the case with yours. I read your paper, but it was a while ago. I was using degree 6 sum of squares because I was talking about these variables tau and what tau squared is. You can show that degree 4 sum of squares does not give the correct scaling. That degree 4 sum of squares thinks the ground state energy is a factor of square root n bigger than it is.
Yeah, I should probably come back and think about it again. Yeah, thanks for a very interesting talk.
Thank you. Thanks for the question.
Sorry, yeah, talking about specific GIJK, if you look at the ground state energy, it's some coefficient times square root n. What is the variance of this coefficient as you average over J?
Oh, I mean, it's going to have some kind of concentration of measure if you draw it from this. So, I mean, this is kind of actually much more general than something to do with SYK. It's more to do just with high dimensional geometry, that you have some function that doesn't vary too much when you change Jij. When you change Jij, the ground state energy can't move too much, just because the change in the ground state energy when you change J is like just how much you change J times these expectation values, and these expectation values are bounded. So then standard concentration of measure arguments tell you that with high probability, it's going to be whatever this value is plus little o of 1, like something that's
so the coefficient varies by order 1, the coefficient varies by order 1 over square root n.
Okay, I don't remember what the coefficient varies. The coefficient in front of the square root n varies by something that's parametrically smaller than 1. I don't remember like whether it's down by 1 over root n or by what, but it's not that like on this model it's square root n and this is 2 square root n. They're all like square root n plus or minus something that's a smaller scaling.
I had another quick question. Is the psi of theta with the theta about the right value, is that supposed to be a good approximation to the ground state wave function? Like not just for the ground state energy, but for the expectation value of other operator?
Probably not. Probably, I mean, it definitely gets some of the expectation values right, but or gets the sum of these right. But like, yeah, whether specific things work out right, I don't know. I think it's more just there's a large entropy in this SYK model. There are many states of the correct order of magnitude. And I think this is just sort of one state of roughly the right energy. And I don't think it necessarily knows much about the true ground state. And I don't know whether you can try and improve this and get closer and closer to the ground state energy. I mean, there's sort of a natural path to try to improve it, which is to say that rather than just doing this naive rotation, you could think about it as an initial Hamiltonian, which is this particular quadratic Hamiltonian, a final Hamiltonian, which is this quartic SYK, and maybe trying to adiabatically evolve the state from one to the other. And perhaps as you do it slower, you can get closer. I haven't thought about that.
When you expect that finding the actual ground state is a very high complexity problem?
I would guess, yeah. So, but it's interesting to me that you can kind of get in the right order of magnitude with a reasonable complexity.
That's because you are aiming for the leading order in n terms.
Yeah,
so,
but I don't know. So so I don't know. Like, I think it's an interest. Like, as you get closer, like, how does the complexity go up? I would expect that the complexity gets. The polynomially, there's probably no way to. I don't know. If I had to guess, my guess would be that. The closer you get the coefficient, the higher the order of polynomial you need. Like, so maybe it's a time polynomial in n, maybe it's like time n squared gets you within this factor, time n to the 4th gets you within like a closer coefficient and so on. But any given polynomial can only get you so close. But that's just a guess.
Could I ask a question, maybe?
Yeah, please.
So we know physically that if you start with SYK and you add in any sort of random quadratic hopping, the ground state is unstable. And I'm wondering if that's maybe something you can see in this context where you add in some arbitrarily small Tij, gamma I, gamma J, and all of a sudden these Gaussian states start working better as witnesses or something. Probably.
Actually, I mean, what I'm going to take a guess, I don't know. So I'll make a guess, and probably this is known in literature, so you can just right away tell me whether the guess is right or wrong. If you look at this way of thinking about it, gamma I, tau I, that H is that, and then you say, oh, we like pretend that the tau are anti-commuting variables, except that tau squared is not 1, but is smaller than 1. I'd guess that if you start adding in a quadratic coupling, that exactly tells you like how big the quadratic coupling should be. So that when the quadratic coupling reaches the same order of magnitude as what you would get by pretending that these tau are anti-commuting this like 1 over root n in front. So I guess that's what would happen. And I think all these methods would know about it. I think these methods would know about it for both upper and lower bounds. Just a guess, but I think they would be able to figure that out. And yeah, you're right. The Gaussian state starts to work, of course, as you add that term in. I would be, very strongly guess that a Gaussian state starts to give a good approximation as you add that term in.
I see. Thanks.
Well, if there are no more questions, let's thank Matt again. And as Nati said, we will have another discussion session at 4 p.m. over time. Okay, let's.
Thank you.